Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is for pre-calculus students, or really any student who is going through a math course and you need kind of a quick review or showcase of the Rational Roots Theorem. Your textbook may call it the Rational Zeros Theorem, which is perfectly fine, but most people call it the Rational Roots Theorem. It is assumed that you've actually seen or been exposed to the Rational Roots Theorem already. This is not a proof of the Rational Roots Theorem. I'm not going to derive the Rational Roots Theorem. I'm just going to quickly kind of rehash what it is, and then we're going to use it. So as you can see on your screen right now, the Rational Roots Theorem deals with a polynomial. F of x is equal to a sub n, x to the n, plus, and you can see the rest of it right there. All of those coefficients are assumed to be integers, and it has to be degree at least 1. And the Rational Roots Theorem states the following. If we have a rational root or a rational zero of our function, then that rational root or rational zero of our polynomial function has to be the ratio of p over q, where p is a factor of the constant a sub 0, and q is a factor of the leading coefficient a sub n. Again, it is assumed that your instructor or professor has covered this in class, possibly even proved it, which is probably a good idea, but depending upon time, they might not be able to. So back to the question at hand, what we're being asked to do here is factor a polynomial function into the product of linear and irreducible quadratic factors. I want to be very clear before I begin this, that I'm not factoring this big polynomial into the product of linear factors which might have complex roots. I am really just factoring it into a bunch of linear and irreducible quadratic factors. This is the first step in factoring when you get to the more advanced levels of algebra. If you don't know what all that mumbo jumbo means, it's not that big of a deal. We'll get to it eventually. Anyhow, what we're looking at is trying to figure out the factors of that leading coefficient, and I'll go ahead and write those down. So we happen to know that 8 has factors 1, 2, 4, and 8. All of those are factors of 8. And then you also look at the constant, and this is a large polynomial. So this constant, luckily, is not highly factorable. I'll go ahead and zoom in on it here. 5 definitely has these two factors right there. And once we get down to that point, we're ready to begin the testing of all the possible rational roots for this polynomial. And by the way, that allows us to factor this polynomial, but that requires you to use something called the remainder and the factor theorems, or basically the factor theorem, honestly, which is assumed that you already know. So that's not what this video is about. So the Rational Roots Theorem tells us that every single rational root of this polynomial has the form p over q, where p is a factor of that constant and q is a factor of the leading coefficient. Let's go ahead and write out the candidate roots. These are possible roots, but I'm going to tell you right now, they're not all going to be roots. They're just all the possible roots. So the candidate roots are all going to be plus or minus as well. That's another thing you have to be careful of. It's going to be plus or minus. We'll start with this, the 1 over 1, 2, 3, and 8. I'm sorry, 1, 2, 4, and 8. There we go. Those are the ratios of the factor 1 over here to all the factors that you see over there with pluses or minuses. Now we're going to go ahead and try the factor 5. That's this guy right here. We'll go ahead and add those in. So we have plus or minus 5 over 1, plus or minus 5 over 2, and so on and so forth. Now, as you can see, this leads to, let's see, 1, 2, 3, 4, 5, 6, 7, 8, but then pluses or minuses. So 16 different roots that could be possible candidate roots, or I should say that are candidate roots for this large polynomial. It's best to clean these up, by the way, as much as possible. There was not much to clean up there. And now we're going to go through and test them using a combination of the remainder theorem and the factor theorem. The remainder theorem tells us that if we have a polynomial and we divide it by x minus c, then the remainder is p of c. And the factor theorem tells us that if we could have divided out x minus c, in other words, if x minus c is a factor of our polynomial, then that c is a zero of that polynomial. So essentially what we're going to do is we're going to see if x minus these candidate roots, each of them, can be factored out. We're going to determine that using synthetic division. And in that process, we're just going to see, is that candidate root an actual zero? If it is, then we know that x minus that number is a factor. My suggestion is to always start with the lowest number and also with integers if at all possible. The other thing to mention before I start is you do need to know synthetic division. I'm assuming that you do. So let's go ahead and start. I'm going to start again with the positive 1. So I'm going to just test plus 1. See if 1 is a root or a zero of our given polynomial. If it is, then x minus 1 is a factor via the remainder theorem. Also via the factor theorem, technically. Be very careful when using synthetic division. You do have to have a placeholder if you have a missing term, that is a power or a degree or a monomial's missing. For example, what if we didn't have x to the 7th there? We'd have a 0 x to the 7th in our synthetic division. Just be very aware of that. Incredibly common for those mistakes to happen. All right, synthetic division. Bring down that 8 and then multiply and write the product right there. Add, multiply, you get the point. I'm just going to continue forward. Now you see, after synthetic division, our very final term here is a 0. That means that our remainder after dividing by x minus 1 is 0. That is, x minus 1 is a factor. Again, because we did synthetic division with a plus 1, we found out that x equals 1 is actually a 0 for that function up there, which means that x minus 1 is a factor. So I'm going to keep a list of those factors. Actually, maybe I will go ahead and box this up in white when we find a 0, or in other words, a factor. Now that I've got to that point, I'm going to see if 1 again will be another 0, because zeros can happen in terms of multiplicity. We could have 1 be a 0 of multiplicity 2, 3, 4, 5, 6, 7, whatever we want, or not what we want, but whatever can possibly be. So let's go ahead and see if 1 is a 0 of multiplicity, for example, 2. Notice that I'm using the same tableau, so I don't have a lot of rewriting that's necessary. There is necessary rewriting if obviously the first 0 that I try, or the first candidate root that I try, doesn't work out, but that first one did work out. So let's try this. Bring down the 8, multiply, and start the whole process again. And you see, we actually arrive at another remainder of 0. That means that we have 1 being a 0 of multiplicity 2. Well, that's great. Now we know that x minus 1 factors out twice. X minus 1 times x minus 1, or x minus 1 squared. So we are really starting to speed up the factoring process here. Let's see if positive 1 is a 0 of multiplicity 3. Again, I can reuse the same tableau. So that's what I'm doing here. Bring down the 8 and start the process. And you can see right here, if I move this 37 up because it's being multiplied by the 1, well, we're not going to get 0. So we're stuck there. But luckily we found 2 of our actual roots using the rational roots theorem. Once you've exhausted the possibility of positive 1 being a 0 of multiplicity 3, I'm going to go ahead at this point and just remove it from our list of possible roots. We've tried out 1 as much as we can. Now, because I have a digital whiteboard, I have the advantage of being able to erase my screen when I need to. So I'm going to erase my previous work here because this didn't work out for me. So I'll go ahead and erase this stuff right here. And I'll start with the tableau that I left off at, or left off with, and we'll go ahead and try the -1. Again, you just bring down that 8, so nothing's really changed there. But now you have to watch your mathematics because you're multiplying by a -1 here to get a -8 there and adding down. Let's go ahead and start the process. Well, this is very nice. We got another 0. -1 is a 0 for this polynomial up here. Now you can see I'm kind of running out of room, but by magic of whiteboard, I'm going to go ahead and erase some stuff and move some stuff up. But just note that I had to be very careful. I actually had to rewind a little bit because I forgot to multiply by this -1 right here. So be very, very careful about that as you go through. I'm going to go ahead and clean the whiteboard right now, or the chalkboard right now. And I'm also going to go ahead and write out my factorization so far. What we had was that 1 was a root of multiplicity 2, which means x minus 1 is a factor twice. So x minus 1 squared is a factor. We also got that -1 was a root because that synthetic division showed us that we ended up with a remainder of 0, which means that -1 is a 0 of our polynomial, which means that x minus a -1 or x plus 1 is a factor. Now we're not done with the x minus a -1. I just want to move things up a little bit. Now that that's done, I do want to mention, as I was erasing this, I just remembered it's probably a good idea to be very careful. It always is a good idea to be very careful with your arithmetic. If you made an arithmetic mistake earlier, it'll propagate through all these computations. So be very, very rigorous with paying attention, or actually a better word is methodical with paying attention to what you're doing. Now, I'm going to see if -1 is a root of multiplicity 2 here. So again, bring down the 8, multiply by a -1, right? Add things up and continue forward. And lo and behold, we get that -1 is a root of multiplicity at least 2. Notice I said at least. It's because we may get it to be a 0 again. But while I have it in front of me, I will go ahead and say, since -1 is yet again another 0, then x minus a -1 or plus 1 is yet again a factor. Notice we now have 4 powers on x. We need to get to 10 powers altogether. So we have a little bit extra work ahead of us. That's okay. Let's go ahead and try that -1 yet again. Well, this is very nice because we find that now -1 is a 0 of multiplicity at least 3. In other words, x plus 1 is a factor 3 times. All right, not too bad. If we're lucky, maybe -1 will be yet again another 0. So let's go ahead and try this out. Okay, so we get to this point right here. As these numbers started growing and getting larger as I was writing them down, I just immediately knew, no, this is not going to work out at all, because there's no way that whatever this result here is, when I take its opposite and put it right there, that summation will be 0. There's just no way that's going to happen. So we've reached the end of the line with our plus or minus 1 possibilities. So I go ahead and reset the tableau. I go up here and I'm going to go ahead and erase that -1 as a candidate root because, well, it's no longer a candidate. We found out that it's not going to work out. Now look at all the other candidate roots we have to try. Now you don't have to try all of them, but you're going to have to go through at least one other candidate root, at least. until you get down to a trinomial. And we'll talk about that when we get down there. But let's see, do we want to try the plus or minus 5? Let's go ahead and try the plus or minus 5. They're nice, clean numbers. Why not? Now, once you get away from the plus or minus 1, the numbers get a little bit ugly. So you'll see that as we do this, 5 times 8 is 40. And then minus that 28 gets us to 12. But then 5 times 12 is a 60. And then plus 70 is 130. And now you can kind of see the pattern here. It's going to get larger and larger. What is that? 500 plus 150 is 650. And you're going to add that. I mean, that's just going to be massive. Large, 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 large. I just have a feeling the plus 5 is not going to work out. It's not that I'll erase it. It's just that right now, as I see it, those numbers are ugly. I'm not going to continue forward. I'm going to try something else. And just for giggles, let's try the negative 5. We might find out very quickly, though, that negative 5 is not going to work, or it's not looking like it's going to work. Yeah, you can see right here, this is just going to get multiplied by 5. Whatever the result is after that new addition, it's going to get multiplied by negative 5 and so on and so forth. So again, I'm not going to bother continuing forward with that one. You get kind of used to this idea of when you see these numbers start to explode, you back off and think, maybe I will ignore that root for right now. I'm not going to erase it. I'm just going to move on from it for the time being. Of the remaining possibilities, probably the next most attractive root will be a plus or a minus 1/2. This guy right here. So let's try the positive 1/2. 1/2 times 8 is 4. Add that to negative 28. The nice thing about the 1/2 is it keeps shrinking the product down so things don't grow out of control. And there we go. That's pretty nice. We actually found out that 1/2 is a 0 because we ended up with a remainder of 0. So therefore, x minus 1/2 must be a factor. Now let's go ahead and test to see if 1/2 is a 0 of multiplicity too. Just continuing with the tableau that we are just arrived at. Well, that is very nice. That is super nice because we find out that 1/2 is a 0 of multiplicity at least 2. And now we'll go ahead and go up to the top and just write x minus 1/2 is a factor at least being squared. And I tend to like, once I get down to 4 terms in my polynomial, and this is what I mentioned earlier is that I was going to talk about this, that each step of the way, what you're doing is you're recognizing this term right before the remainder is the constant. Here's the x to the first, the coefficient of x squared, and the coefficient of x cubed. And you might be able to, although you can't in this case, but it may be somewhat obvious that you can factor by grouping here. For example, if I wrote this out as 8x cubed minus 20x squared plus 48x minus 20, you might be able to factor by grouping. In this case, you cannot, but it's always a good idea to just take a look and see if you can. But like I said, in this case, we just can't do that factorization. So we'll continue forward with the rational roots theorem one more time. And let me zoom out because I think I'm at the bottom of my page, but I think I can fit this computation in there. Let's see if 1/2 again is a 0 for this polynomial. That is, we're checking to see if 1/2 is a root of multiplicity at least 3. Bringing down the 8, multiplying by 1/2, and going through all the process we had before. And lucky us, look at that. We find that 1/2 is yet another 0. So we have 1/2 as a 0 of multiplicity 3, and we can power up that factor to a third power as well. And now looking at the factorization, we're not done, but we're pretty darn close because just recognizing what we mentioned a moment ago, this piece right here tells us our remaining factor is 8x squared minus 16x plus 40. Now note, you could factor an 8 out of all of those terms, and you could see that that is definitely not factorable. No matter how you try to factor that, that is not factorable, but that's okay. Because what you can do at this point is you could leave it alone. That's called an irreducible quadratic. And so I'll leave that irreducible, non-factorable quadratic. It's non-factorable over the real number system is really what it is. I'm going to leave that alone, and I'm going to go ahead and tag it onto this business here. So I'll have a times 8 times x squared, and I think it was minus a 2x. Yeah, minus 2x plus 5. I would not leave my answer like this because we're used to writing constants as leading coefficients, but there's a little trick you could do here that you may not realize. It is perfectly fine to leave your answer as 8 times x minus 1 squared times x plus 1 cubed, and so on and so forth. However, if you didn't know, 8 is 2 times 2 times 2. And so you could actually take each of these factors right here. Since they have 1/2, I don't like fractions too much. So I could imagine that's x minus 1/2 times x minus 1/2 times x minus 1/2. It's not that big of an imagination there, right? You could totally figure that part out. But remember, we have this 8 sitting out front, which you can break into 2 times 2 times 2. If you distribute that 2 times 2 times 2 into each of these factors, you'll get that those factors are actually 2x minus 1. So each of them are 2x minus 1s. So this gets rid of the 8 out front and simultaneously allows us to get rid of that silly fraction. I only mention this because some people will look at an answer key or something like that and say, man, how come I got fractions and they didn't? Or how come I got an 8 out front and they didn't? And that's why it's true. That's why what the person did in the background. And it's always a smart idea if you have that ability to do that. So here we go. That is the full factorization into linear and irreducible quadratic factors for that big old polynomial using the rational roots theorem. I hope this helped out, and I hope you have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.